This is a relatively rapid rundown on a high-density interconnect. So kind of before I get started, how many here are printed circuit designers that use the micro-via or high-density interconnect currently? Okay, good. Well, like I said, I only have a third of you, so I'm not going to ask the questions again of, or how many are looking to have to use it in the future, you might say. Well, for people like myself that work a lot with the semiconductor industry, since the semiconductor industry is at 7 nanometers, the famous phrase will be, if you're not using HDI today, you will be very soon. And the reason is that the rise time of modern integrated circuits require that everything be a transmission line. And because of that, and the pitch is shrinking as they increase the number of gates. And with that shorter rise and fall time, they have to have more grounding pins. So we're going from a maximum of 2,000 pins. I've just seen a latest generation of 3,700 pins. And Texas Instruments showed me a 5,500 pin device. So you get the pleasure in a few years of working with up to 5,000 pins as a device, because you would think that with 2 billion transistors, you could complete everything on the chip. But you keep adding more functionality and wider bus sizes, and the number of pins signal pins keep going up, and they have to have more and more ground pins for the signal integrity. And because the semiconductor people don't like to pay for transmission lines on their packages, they use up the critical length, so that when you buy the chip, you have to be 100% transmission line on your design, even if the clock is slow, because it has nothing to do with clock rate, it has to do with the rise and fall time. And these tiny transistors turn on and off very rapidly. So consequently, they're transmission lines whether you want them or not. Because I've had people complain with a 100 megahertz clock, why do I have so much noise? I said, well, did you design with transmission lines? No, I don't need it. I only have 10 or 20 megahertz. I said, no, it's got nothing to do with the clock. What's your rise time? Oh, well, 1/10 of a picosecond. Well, that's why, But he said, the last chip, didn't have that problem. I said, yeah, but the last chip was 200, 300 nanometer transistors. These are 7 nanometer transistors. So look at the specs, the turn on and turn off time. The clock hasn't changed, but your rise time has. And that's one of the reasons why we say that if you're not used to signal integrity problems today, wait a year or two, and then you'll be in the center of a lot of signal integrity problems. So you can read all of that. So Altium just told me that they sent all of you all of these slides, because I was complaining that you should have got them 2 weeks ago. So if you would check your email, there's 8 files from Altium, and it's these slides. So at lunch, or if you've got a tablet or something, you can actually download the slides while we're here, or at break, or at lunch for use. Otherwise, they weren't going to send you the slides for 3 weeks, which that's way too big a disconnect between what we were here and having the slides 3 weeks kind of thing. So this is what we're broken up into with our tea and coffee break 9:40, and lunch at about just before noon in the afternoon. And we're supposed to finish up at nearly 1700 this evening. That's just a short summary. Unfortunately, like I said, I don't think Altium had this kind of detail in the thing, which I wanted you to have this ahead of time. Mainly because you can look over the slides and see if you had questions and a chance to think about the questions a while before we're actually here. The one question I have is, how many have downloaded the handbook on HDI technology? It's 820 pages. It's free, so you don't have to buy it. There's the URL. It's just http hdIhandbook.com, no www. And you can download that from iConnect 007. How many know about the Altium HDI guidebook? That's also free, but not easy to find on Altium. This is a second generation. It's a 60-page guidebook that is not in the HDI handbook. The HDI handbook I wrote in 2009. This one I wrote in 2019. So, and so although you go to altium.com, it's not easy to find at all. I don't know why. It's just, because I went there and I can't find it. But I know it's there because I've downloaded it. But it's somewhere over in the blog guidebook section, which is very difficult to get to. But I recommend you download this. We will not be covering this material or the handbook material because you can read and download. Today is the material I didn't write in the books because people have a limit on how big these books are. But this technology keeps increasing and becoming more complex year by year. So it's tough to keep up on it. It's starting to break if you want to thumb through what's in. And the reason that this Altium one goes into the Altium Designer software using HDI, which there are some cautions. I don't want to berate Altium, but there are some cautions about using Altium for HDI design that are in this guidebook. There's potentially enough traps in HDI design. We don't need to go into the problems of the CAD tools issue part of it. So with that, let me bring up the next section. So for many of you, you've already gone past this decision. Do you need it? A lot of people don't have to use it just yet and may never have to use the high-density interconnect. If the pitches aren't shrinking and you can get 1.27 millimeter devices on ball grid arrays, if you don't have signal integrity or other issues like that, you have plenty of room and don't need to worry about shrinking the size. But for the rest of you, we're going to talk a little bit about the design metrics. Anybody you here ever used design metrics or measures of performance of design? So one of my roles in the last 50 years I've been in this business is I was the design manager for Hewlett-Packard worldwide. And one of the issues we have, I worked for the vice president in Hewlett-Packard that had both integrated circuit design and production and printed circuit design and production, kind of all the process areas. And they were used to, in the integrated circuit design, to measures of performance. Printed circuits didn't have any measures of performance, so they required that we define what it is that we are doing. And especially, how is the performance of each designer? And in terms of a measurable quantity, not our opinion, but what do their designs look like? So they're measures of performance, because we want to improve that measure of performance, and it's tied to their salary. So that measure of performance is very important. But also in Hewlett-Packard, after 5 years, you're rotated into IC design, and IC designers come into printed circuit design. So we rotate our designers between the two fields. Consequently, they're all paid at the IC design salary, not the printed circuit design salary, because there's a lot of demand that they constantly learn newer techniques. And spending time on integrated circuit design, when you get into printed circuit design, there's a lot of complaints that in printed circuits, they don't have the tools and techniques that IC has. And we agree. So we're fairly critical of the EDA vendors that don't evolve their integrated circuit tools down into the printed circuit arena. And it really comes to, we like to charge big numbers, big prices for IC tools because the IC guys can pay it, and nobody in printed circuit will pay that amount of money. They said, well, it's a sunk cost. Now that you've already written the software, you don't have to charge the printed circuit the same amount of money you charge the integrated circuit people. No, they don't. They want to. So there's complex business reasons, but not technical reasons why IC tools aren't available to printed circuit users. But at Hewlett-Packard, we wrote our own IC tools. So it was easy for us to adapt them to support printed circuit tools. In fact, most of the Mentor software was licensed from Hewlett-Packard. Mentor, which is a big IC, as well as Cadence. And the reason was we had a concept of Silicon Write the first time, which people from all over the world used to come and visit us to talk about how can you do complex Silicon Write on the first pass every time. We saw it's because of these tools and these analysis techniques that we have. So one of the things that I'll emphasize today over and over again is that in high-performance electronics, circuits, components, materials, stack-up processes are all interlinked. I don't know if you knew that, but everything in this arena ties together. So if you change the line width, you'll change characteristic impedance. But if you change spacing, you may change crosstalk. But if you change material, you'll change impedance and crosstalk. And so what I have a problem with this diagram is trying to illustrate the fact that what happens over here in manufacturing affects a design over here. So as an example, any of you here use thermal modeling on your PC boards? You don't? Well, on especially 5G and higher RF and other circuits, the whole problem of cooling has become a big issue. And so you have these thermal modeling tools, three-dimensionally, that shows what's happening to the temperature of the PC board and the cooling effect. And so there's quite a drastic range of temperatures on the printed circuit board. But if you go to the signal integrity tool, it assumes the printed circuit board is all at one temperature. And the modeling tool thermally just showed that there's a 50 degrees Celsius difference across the PC board. But the signal integrity tool ignores that. Well, the dielectric constant and dissipation factor of material changes with temperature, which means that there is enormous amount of signal integrity error because they don't compensate for the temperature changes that they have access to in their thermal model, but they haven't bothered to integrate the mechanical thermal to the electrical signal integrity. In integrated circuits, we have those models three-dimensionally interchange that data. So it's much more accurate. Very inaccurate in the printed circuit world because there's no such thing as a PC board that sits at room temperature, fundamentally. It would be ideal if there was, but the thermal tools will show you that that doesn't happen. This is a crude estimate. If anybody has any ideas how I could illustrate this better, I'd love to see you break. The main thing that drives most people to high-density interconnect is density. And that's because the silicon integration, we have more I/O and we have a finer pitch. I'm now working with people where the pitch of the device is 0.08 millimeters. So what are some of the finest pitch some of you are working with? 0.35 millimeter, 0.3 millimeter, 0.4 millimeter. Anybody here got a new number that's very small? The smallest I've seen is 0.08 millimeter. So if you're working with 1 millimeter, you got a lot to learn to figure out how to work at 0.08 millimeter pitch for each device. And that's 3,700 pins at 0.08 millimeters. So it's a piece of silicon about this big. It's almost 2.5 centimeters across. One piece of silicon. It's got 5 billion transistors on it. And it's 180 watts. So it draws nearly 200 amps at a low voltage. So it's an enormous cooling problem, but it's also an enormous signal integrity problem with that many devices. And that's a relatively old device. Like I said, TI showed me some 5,500 pin devices coming down in a year or two. So it's just going to keep. The other thing is simply with the faster rise time, you have to worry about time of flight. So you want to put parts closer together to minimize the signal integrity issues. And strangely enough, with the larger bus sizes, there are more and more discretes being used today than we used in the past, even with analog. So actually the number of discretes are going up. And things are just getting smaller and thinner, as well as dealing with lead-free assembly. So some of the components, that are driving this, the surface mount devices, but anyone here work with a ceramic column grid array? The European Space Agency uses a ceramic column grid array. It's a 2,000 pin device for space work here in Europe for the European Space Program. You've got micro ball grid array. This 0.08 millimeter pitch, that is a flip chip on a board. Anyone here work with flip chip? Well, instead of putting the flip chip on a substrate, they put the flip chip directly on the PC board and save that whole layer, and they underfill it. And so consequently, you're connecting directly into the silicon, which is why it's 0.08 millimeter pitch, because normally the package will fan that out to a 1 millimeter or 0.8 millimeter or 0.65 or 0.5. But you have to pay for that. And the semiconductor people hate the printed circuit people because that may be a 50-cent chip, but the package costs $5. So the package costs 10 times more than the silicon. And the semiconductor people don't like the fact that they're really expensive chips. They have to pay even more money to fan it out for the printed circuit board. So they would like to get rid of printed circuit boards, but they've been saying that for the 50 years I've been in electronics, and it's not likely to happen because we keep adding more functionality with that. So these are, so if this slide right here is 20 years old. So I've been using this same slide for 20 years because, that 0.25 millimeter, that's a flip chip. That's the pattern on the PC board for the flip chip, the direct silicon. But that's for automotive. It's in the what's the GM car here? Not Edsel, it's the GM car, Opel. So that's in your Opel. The Opel for the last 20 years has had technology greater than the military or space has had because they take the engine control and put it right on a very thin printed circuit board. And it's more reliable than using a ceramic, hermetically sealed military package. I've seen the data from General Motors. And 0.4 now is pretty decent. These 0.4 are now 0.35 and 0.3 millimeter pitch. And there's some 0.4, 0.8 millimeter, nearly 1,000 pins at 0.65, 500 pins at 0.5. Like I said, this is 20 years ago. we had these. Today, I'm retired, so I don't make the printed circuit boards have access to these kinds of photos. But I don't need to, because there's a continuum of electronics. And if possible, don't use the finer pitches if you can get away with it, because it's harder to design. But you many times have no choice. When they went to lead-free, they promised the US military that the military chips would be 1 millimeter and 1.27 millimeter pitch. Never delivered. All of the military chips came back at 0.8 and 0.65. And so the military was stuck all of a sudden that they couldn't use through holes. They had to go to microvias. And so the military and space people were kicking and screaming into HDI. Not their choice at all. They prefer the bigger packages. The semiconductor industry said, because of mobile phones and automobiles, we're only going to make one package. It's going to be the small one. We're not going to make a big package just for you. And the other thing that caused was they wanted them to be tin lead. And they said, no, since the mobile phones are lead-free, the packages have to be lead-free, which forces the military to reball all of their components with tin lead connections that they're still allowed to use, and not the lead-free ones. So this will continue to go on. Like, this is one of the latest Intel. And one of the latest Intel 1288 pins it's non-symmetrical and multiple grids on the same. And the color up there, green is ground, blue is signal, and red is power. So you notice it's not symmetrical at all. And that's also becoming more and more common. They can't afford to make these complex chips symmetrical. And so consequently, they have, like I say, a 0.8 millimeter staggered grid, a 0.7 millimeter depopulated, and a 0.7 millimeter matrix. So it's a lot of fun. And they could kind of go on and on with what packages are coming out of. We particularly like, this is a particularly good design right here, because these people thought about and gave you a place for a drilled through hole. When they go like that, you're kind of stuck. You've got to use all microvias. But if they're smart enough to give you areas for very small drilled holes, you don't have to use HDI and microvias. But it's purely up to the packaging people in terms of if they do this or not. And here is this ceramic column grid array. These columns, these are 95% lead. So they are exempt from the European standard on lead-free. So European does allow lead in electronics, but only in semiconductor. And the reason was, if they forbid that, there'd be nothing flying and nothing driving. Because the medical, military, and aerospace has not found suitable substitutes for lead in terms of ductility. It looks like we're going to be able to replace those lead columns with copper columns, which is great, good conductivity. But right now, the military packages, communication packages that are on ceramic are still lead, pure lead column. You just don't ever want to have to do rework on that device, because you will melt the columns, and I don't know how you ever get the columns back. That's a tough one. And so this is an older slide, but if you use field programmable gate arrays, FPGAs, which are very, very popular with electrical engineers, they're coming down at 1200, 1508, 1696, and newer ones are over 2,000 pins. like I said, some of the next generation ones are 3,000 pins and 5,000 pins. So the driver of just number of pins and wiring them all out is pretty excessive. So if nothing else from this course, unfortunately, what I'm going to tell you the next 8 hours is that you have to unlearn how you design multilayers. That if you came up double-sided multilayer, when you got to HDI, forget everything you learned about multilayers, because in HDI, the right way to do it is different than the multi way of doing it. And it took us 15 years to learn that. At Hewlett-Packard, we developed the HDI technology in 1982, so it's been nearly 40 years for me using HDI. And for the first 15 years, we treated the small micro vias as just a small through-hole via in terms of our brain. And that's not the right way you'll see throughout the day. You got to forget a lot of the stuff you learned about multilayer and back up and rethink the whole layout and stack up with the PC board. Now you can use the laser drilled micro vias as just another via. It doesn't hurt you. It costs you a lot of money. So one of the tenets that I'll show you over and over again is that if you use HDI properly, your complex PC boards will cost less, not more. But the convert wisdom is, well, if you're going to use HDI, be prepared to pay 20% more. If you do, you've done it wrong. If you do it the right way, you'll pay 20 to 50% less. And so the last session today, I'll go over 3 or 4 excellent case studies in which we took 24-layer high-speed multi-layers and using HDI made it 12 layers. Or we took an 18-layer aerospace board and made it 8 layers. And since most of this is not FR4, but low-loss material, going from 18 layers to 8 layers is more than half the cost. The price dropped in half. So anybody that tells you that HDI costs too much, don't listen to them too much, because they don't know what they're talking about. They're still doing it the wrong way. And hopefully, you'll take away from this class some of the ideas of how you're supposed to rethink that you would never think of doing with a conventional multilayer, that now you must think about doing if you will want to have the higher performance or the lower cost. Now, like I said, you can ignore me. You don't have to do it that way. You can pay more money and it'll still work. But believe me, if it's half the number of layers, the signal integrity and a lot of other problems go away pretty quickly compared to the other. And especially using lead-free soldering. If the board has half the number of layers and is much thinner, it's going to be much easier to solder. As an example, this is Xilinx 1704. This is actually out of the Xilinx manual in terms of how to route that. Okay, but they talk about 6 signal layers. I do it in 2 signal layers. So you can follow Xilinx and do it 6 layers with reference, or you can do it my way and use only 2 signal layers. My board costs half as much as the Xilinx method of doing it. And mine works better electrically than theirs does. So you have your choice. Nobody's going to look over your shoulder and realize that you could have saved the company, a lot of money had you done it the right way. You can do it any way you like. So today is mostly about microvia technology, or these little tiny guys right here. And believe it or not, in North America, we have people that mechanically drill these. Do you have any of that in Europe? Here, where the companies actually mechanically drill the blind via? We actually have a couple companies that have no lasers. They mechanically drill these things, which is not easy, but does work. So a little bit into the metrics. There's not a clock around here, is there? I need a timer. Can't think. Anyway, so a little about the metrics. These are some of the metrics we use in design. Have you ever heard of layout efficiency? Layout efficiency is the amount of space on a layer that you have used compared to the total amount of space available on that layer. What would you guess is an average layout efficiency for a good designer? Anybody here want to venture a guess? What % of that surface on a layer can you use? Anybody wonder? Well, most people tell me they think 25 or 30%. You know, would you believe it's only 6 to 8%? Which, if you think that's incredibly low, you're right. It's incredibly low, and it's an extremely poor job. Not because they're not doing the best. They simply, that's the layout efficiency of a multi-layer, is 6 to 8%. When we go over the case study, we'll go from PC boards that were 6 to 8% layout efficiency to, in properly designed HDI, they are 18% to 32% layout efficiency, 4 to 6 times greater density on the same layer. Well, if you can put 4 to 6 times more traces and not violate power integrity and signal integrity, then you need fewer signal layers. And that's part of the reason why you have these measures of performance. Anybody ever heard of routability predictor? Another one you should be important. That's an algorithm that tells you how much you can utilize an auto router or how much is going to have to be handcrafted. Very important measure of performance. A lot of times these things are measured in inches per square inch or centimeters per square centimeter. And it's relatively easy to get from anybody's CAD tool, including Altium, what the actual, if you highlight just one signal layer and then hit the button in terms of the report of what's the actual routes, only on, of all the nets, only on that layer, it'll come back and give you the distance, which you can then divide up to figure out what your layout efficiency is for that layer. For PC boards, again, it's centimeters per square centimeter, or centimeters, or number of traces per square centimeter are measures of performance. With HDI, you should be able to get nearly 120 traces per square inch, or the equivalent per centimeter. Most of you, because of multi-layer, are only getting 60 or 40, but you should be getting 120 kind of thing. And in assembly, they use the things of average parts per square centimeter and average pins per square centimeter. These down here are universally used a lot and usually show up in your reports when you ask for a report on the design. But monitoring these numbers and implementing some of the newer metrics are measures of performance. I actually use them to provide for bonuses and salary, because those designers and engineers that can get higher density, still meeting the boundary conditions of signal integrity and size, are going to cost us less to manufacture and assemble the product. And so they're worth more than a designer engineer that doesn't know how to do high density or signal integrity. But those are then, I'm responsible for making sure they have the training or the tools to constantly improve their performance. So everybody's working at the maximum performance. So this is one reason why I talk about 0.8 millimeter pitch. This is the packaging interposers from feature sizes in microns and pitch on this axis. You have BGAs, chip scale packages, and direct chip attachment. And so I work a lot down here at 0.1, 0.2, 0.25 millimeter, and have been working down here for the last 30 years. We started doing this stuff nearly 30 years ago. usually on the higher performance computers, not personal computers, but most of the mobile phones from Apple are down here now as well. I've built over 800 million iPhones in my career working for Foxconn. So I know a lot about iPhones, more than I wish to know about iPhones, because I had to build them. You may love an iPhone. I hate them because Apple gives us 17 handcrafted iPhones, and I'm supposed to make 10 million a month of them from their 17 prototypes that were handcrafted. And that's a lot of work to go from 17 handcrafted to 10 million of units. You have to totally re-engineer it to make it manufacturable. The Apple is creative, but they're not manufacturable. So to manufacture them, I have to have 82,000 teenagers sitting big assembly line, doing it by hand because we can't use robots and other things. They're too complicated to be automated. It has to be built by hand. So we're definitely trying to teach Apple how to design for manufacturing and how to design for robot assembly, so that we can, we don't need 80,000 teenagers to make iPhones anymore. That's one reason why they'll never make iPhones in Europe or North America. Because, we can't find 80,000 teenagers willing to live in a dormitory and not have a car and everything. We can in China, but we can't here. The size of the parking lot alone would be massive in size. So most of also today is about talking about this guy. This is the guy that we have to get rid of to replace him with this little guy right there. So it's to take that big via and replace it with a small one, and then use the space for more components or more traces or a serpentine routing for terminations. This is what today is really about. And eliminating the Swiss cheese effect on your power and ground planes. Underneath the BGA, we've turned that reference plane into Swiss cheese by holes like this going all the way through it. So we have enormous power drops and problems with current within the BGA because we've eliminated all the copper. And that's a big problem with fine pitch, because you have to keep the keep out. We've got no copper left to transmit. So consequently, the temperature rise is very extreme, which leads to all kinds of power integrity and signal integrity problems. So one term that I use, you've probably never heard of, is a connect. And a connect is an SMT pad, a trace, and a via pad. So those three elements right there is what I call a connect. I don't like to use pads and traces because they don't really mean anything unless you're talking about transmission lines. If you're talking about density, it doesn't help at all. Because if you take a centimeter or a couple of centimeters, there's only so many of these connects that you could put into that space with the spacing rules you've selected. And once that's full, you've used up all the surface area. And that is this line right here in blue. So you notice this is average pins per part. And this is parts per square centimeter, or be parts per square inch. It's logarithmic. And this line right here is the maximum number of connects you can get with a mechanically drilled hole. So this area down here is multi-layer and through-hole construction. This area up here is HDI. So it makes it very simple. Do I need HDI? Well, how big is your board? How many parts do you have? And how many pins, including test pins, does it have? Are you on this side of the map or this side of the map? If you're over here, it's a conventional multilayer. If you're over here, it's an HDI board. And the reason is because once you hit this wall right here, there's no more room for any more drilled holes. You just ran out of room. It's what we call via starvation. If any of you ever kind of run into your placement and now you're trying to connect, and all of a sudden you ran out of places to put vias. You've hit this wall. Because unfortunately, bosses tell you, do it this way without looking at the numbers. And you're up here, and they tell you, you got to do it as a 12-layer multilayer. Well, they don't know what they're talking about, And yet it's your fault that you didn't do it the way they told you, but they told you something that's impossible. The circuitry is actually up here somewhere, and they're telling you to use the old technology. Well, you can't do it. So when I'm involved in consulting, the first thing I ask is, where is this board on this map? Are you over here or over here? And usually they're over here, but they're trying to make a technology down here work, and it won't work, which is why they're stuck. So a lot of today is, how do you jump over this wall? If you know that there's a density wall coming, how do you, instead of smacking into it, how do you jump over it? Because if you look at, like the term I'm using here, pins per square inch, as you start getting to very, very complex PC boards, the number of signal layers starts going up exponentially. So multi-layers are okay down here, but if you're trying to do it with these fine pin parts, 2,000 pins, you're going to end up with 24 layers, or 30 layers, or 36 layers. And you don't want to have to design that PC board, because that's a devil of a device to actually solder and get up to temperature for lead-free reflow. And believe me, it's not going to be reliable. You can, in fact, get it through assembly, but it will fail in the field. You'll probably lose your job. Your company may go bankrupt because you're doing something that you should not be doing. And it's because these curves all turn up. So this is the through-hole multilayer chart. This is the HDI chart. It goes from 280, then it goes to 500, up to 25,000. So this chart goes all the way around this room to 25,000 pins per square inch. 25,000 pins per square inch is the density of the silicon. And like I said, if you put the silicon directly on the board, then that's the package you have to design for. But you notice here, the number of layers are 4, 8, and 12 in terms of number of signal layers. It's not 24, 30, 36. And that's simply because HDI offers the opportunity for 3 to 4 to 5 times higher density with the same number of signal layers. And so the IPC convention is this 1 plus n plus 1, where the numbers, how many build up top, how many build up the bottom, and 1 plus n, 2 plus n, on and on. So the problem we ended up with was that people wanted to know, well, how much is this HDI going to cost if I have to use 2 build-up or 3 build-up? The problem was that fabricators typically said, well, design the board and send us the blueprints, and we'll quote it. And your answer is, no, I haven't started yet. I want to know what it's going to cost before I start. And they say, well, we can't price it until you completely finish the design. So nobody's getting anywhere. So I took a lot of data and created these construction, and I referenced them to the multilayer, which we all understand, this thing right here. So it has two measures. Density is the average pins per square inch, and relative cost is not in euros. It's relative cost. So what it is, it's based on the cost of an 8-layer through-hole. So whatever you pay for an 8-layer through-hole multilayer, that's 1.0. And so this is a ratio and a percentage. It's not a direct cost. You got to multiply it by whatever you pay for an 8-layer. But you can see over here, so I was working with this 20-layer. It has a density of 105, and we chose to use this construction. And so you can see that, we used an 8-layer. Well, the relative cost went from 5 to 1.5. So there was an 80% lower cost using the HDI. So this is relatively good first pass at, well, what should the construction look like? And so this has actually been formalized more. But you can take this chart to a fabricator and say, hey, please fill in the numbers for your company, how you do it, so that I, a designer, can look at this and kind of get a first pass. What construction should I use? Later on today, we'll show you how to calculate the number of signal layers. So depending on your number of voltage rails and whether or not you're using power ground pairs and things like that, you can add the number of signal layers to the power distribution layers to have. But here you can look at, well, should I have a simple HDI? Should I have a tube build-up? Should the core layer be an additional lamination? Because as you go out this chart, it becomes more expensive, the construction. But and so you want to figure out if this is going to cost us more, how much more can I tell the boss from an estimate point of view is it going to cost me? And if you want to stack the vias, then it enormously drops in the number of layers because, again, it's the highest density. But it's also the biggest problem in terms of reliability. So to stack vias like this, you want to do that very cautiously. Anybody here stack vias? Anybody here over too high on the stacks? Because those are massively failing in the field, both in automotive and military and aerospace. We're desperately trying to figure out why. We think it's the z-axis expansion of the material. But above a too high stack, review some of the IPC reliability publications about how to do that very, very cautiously. But it's also backed by the European Space Agency, that the European Space Agency is restricting a maximum of 2 stack. You're not allowed to stack any more than 2 layers. Then you have to move over, and you can stack 2, and you can move over and stack 2. But you cannot stack 3, you cannot stack 4, cannot stack 5. Now, they do it in the iPhone, but that's not high reliability, because by the time you've owned an iPhone or a Samsung phone for a year or two, you've dropped it in the ground in the toilet, or it simply doesn't have the feature. And they typically get turned in and recycled 2 to 3 years. So they have a 3-year life, not the same as a medical device or something like that that's 20 years, or a military device that has to be 25 to 30 years, or an automotive that must be at least 6 to 10 years for warranty. The automotive people don't like electronics to fail while it's under warranty. It's kind of your problem if it fails outside of warranty, but under warranty, it's their problem. And so, we don't need to talk about, kind of typical microvias. These are our typical microvias. This is what we call a skip via because it goes down 2 layers. As long as you don't violate the aspect ratio, you can go down to sometimes several layers and don't have to, have a buildup layer here if you could skip that. This one right here is hard to see because this is a G-Tech material, which is a 5G material. It's thermoplastic, thermoset, low loss. Really difficult to work with, but anybody familiar with G-Tech, the old, I'm trying to think of a Ventec equivalent. Well, the only equivalent is the Megtran 6 and Megtran 7 material, the expensive materials. So, we're going to talk different aspects of how this guy and this guy replaces this guy and this guy. And the whole day is really spent in how to get rid of these big vias because they occupy the space. And these are the ones that will fail first. The through holes always fail before the microvia. So the fewer of these you use, the higher the reliability, but also the more space you have for routing or components. So this is an interesting slide from the Japanese. It's interesting, the Japanese claim they invented microvias in 1997, 98, and 2000. And it was interesting because I showed them samples of our Hewlett-Packard microvias manufactured in 1982. I said, well, you guys invented it in 97. How come I've got all these samples from 1980? And they look at them and kind of suck in their breath and said, where'd you get this? I said, we've been manufacturing these since 1982 in our computers, you know? And they said, well, nobody ever told us in Japan about this. You know, we invented it in 97. I said, well, actually, you invented it in 1990 at IBM, not 97. 97 is when you start using lasers, but IBM in Japan, Yasu, was using it in 1990 for Intel 286. I said, but the Germans had it, were using it at Siemens in 1987 at Siemens, and we were using it in 1982 in North America, kind of thing. So I'm afraid to tell the Japanese they're last to have discovered microvias, not the first. And go back and read some of the Siemens technical papers from the late 80s about Siemens computers, and they'll see some of that. This is just kind of expected growth rate and things like that, but also in the backplanes, moving from press fit over to surface mount and microvia backplanes for devices is very common. So this one right here is a terahertz router for central telephone switches. And you can't see it, but this is that G-Tech. But on this side of this backplane, the boards plug in this way, but on the other side, the boards plug in opposite. So it's called a midplane. Yeah, here it is. So on one side, the boards go that way, but on the other side, their boards are at 90 degrees. So this is much more effective than a backplane because like this, the interconnect now, the interconnect you see is very short. With a backplane, a conventional backplane, we got long traces in the backplane running all over the place. With a midplane, we have very short connection between boards on one side and boards on the other side. And that's because of the 5G and the high frequencies involved here, we have to make all the critical traces as short as possible in those constructions. And so here are some of the microvia. The purple, the blue is a drilled hole. The purple is a back drilled, a hole that's been drilled and then back drilled to make a short stub. And the dotted is the HDI. And you can see the dB loss as you go up in thickness and go up in frequency, you know, how the microvias are much less loss than the mechanically drilled in back drilling. So back drilling is not a good idea. I mean, back drilling is very expensive, is very restrictive on design. And what you're trying to achieve is a blind via. Well, if you're trying to achieve a blind via, just design in a blind via for laser. Don't design in a mechanical hole that you then have to back drill out because you're going to pay a lot of money for that. And you're still going to end up with much less signal integrity performance in the long run with it. Which is why, so now we have all of these surface mount type of headers that are designed not to use through holes, but to use surface mount connections. Things like that, there are 21 gigabit, 10 gigabit per second surface mount connectors. So this is like, say, press fit backplanes at 5 gigabits per second, the dB loss all the way down to a blind via midplane with about 5 dB loss compared to over 14 dB loss. And you know, these are some of like the microvia backplane design. So with that, another thing that we'll address today is the way you do a breakout on a conventional multilayer. You can do that with microvias, but you're wasting your money. And so one of the things we have is that since the microvias are so small, you can swing them around like that. So instead of using a north, south, east, west breakout, you've got enough room to swing them around and to save the space. And it's your choice of which channel size you use, A, B, or C, because where are you going to put that microvia? You can put it in the pad, adjacent to the pad, or right next to the pad. And so we call that inset via, partial via and pad, and offset center via and pad, in terms of where that blind via goes with respect to the pad. You know, you can't do this in mechanical drilling, but with laser drilling, this is perfectly okay. What you don't want to do is you don't want to put that in the very center of the pad. That's a no-no. I'll show you later. You never want a via and pad to be in the very, very center of the pad. You always want it slightly offset. We'll show you some other slides about that. One of the things you can do because of that is that you can now do a ground flood on your surface. And so because you don't have these big dog bone breakouts, you can actually do a complete ground flood of the surface. Later on, you'll see the advantage of that. So one of the concepts is looking at channels. And channels is a concept of the semiconductor manufacturer orients his power and ground pins in some kind of geometric fashion. And if you can, they don't tell you what it is, but if you look at the pinout where you're doing the library, you can see a pattern. And if you can see a row of ground pins, well, you can select those as being the ones that will have the microvias. So this is a conventional breakout for through holes. There's 132 possible routes, one trace between the vias, plus 20 traces in the center areas here. So it takes 8 layers and 5 reference planes to fan out this part. But if you pick an area like across here that are going to be blind vias, not through holes, then you add additional escapes. You add 48 additional escape connections, and this whole thing can be routed out in 2 signal layers with 2 reference. So instead of 5 signal, instead of the other one. So this is beginning to understand why you got to unlearn how you did it in a multilayer. Because a multilayer with just through holes, you're restricted geometrically. Now you've added another construction element, the very, very tiny blind via. You need to rethink, how do I do breakout? And how can I take advantage of this technology, not just in breakout, but in the whole design? And so they can be cross-shaped, they can be L-shaped, or they can be diagonal, depending on how the IC people have situated either their power or their ground in terms of geometric. Once you figure out that pattern, that's the first place to put the blind vias, because now you have methods of signal escapes inside the PC board, because where the blind vias on the surface underneath them, that's open now for routing and more escapes, which you can't do on a through hole system. The hole goes all the way through the board, but the blind via doesn't. And so the whole thing on channel rounds, so this is actually that same device, no breakouts at all, because all the vias are in the pad. And so one thing is that layer 2 is not ground, because ground is now layer 1 along with signal. They just bring that ground plane up. So in this one, there's already 2 less layers, because n minus 1 and 2 are gone. They've been merged back up into the first layer. So you have SMT and ground, which means that you might consider power as layer 2. And now all of the ground and power don't go down to the inside of the PC board. So now the inside of the PC board has 8 times more space for signal routing because you don't have a forest of holes that are there. And even with a small breakout, that's possible. Then on the opposite side, when you have through holes, there's just a forest of holes, so your components have to go outside. But once you use the blind vias, you can now put components inside the footprint of the VGA, and which many people do. They put their pull-up and pull-down resistors, decoupling capacitors right inside the footprint. It's not outside. It's on the opposite side of the board, taking advantage of the space they've saved. And so, like I said, some of the best ones are ground on the surface and power is layer 2. If you go signal in layer 2, because transmission lines, that's going to have to be a lot deeper, kind of thing. And the interesting thing here is that this never violated the buried capacitance patents, because the buried capacitance patents talked about a core, and this is prepreg. And so people that used it this way never had to buy the license for the millions of dollars to use buried capacitance. The buried capacitance were free, kind of thing. But the other ones that even though they were using microvias, they still had to pay a royalty to use buried capacitance. Now, the buried capacitance patents have been invalidated because they stole, the patent holders stole the ideas from another company. But we didn't find out about that until the company fired the guy that has the buried capacitance patent. And after they fired him, he went back and told the lawyers that he stole the idea from another patent. When they looked it up, yep. And so the courts threw the whole thing out. So the company that required $1 million license went bankrupt because they had to pay all of the royalties back to the people because they had broken the law when they filed the patents. So the end of the story is make sure you know who has the goods on your patents. And if there's shenanigans, don't fire them. Because if they go blabbing that the patent's invalid, had to give all the money back. With that, where are we in terms of time?